In the past couple of sections, we've seen how to set up an integral in terms of a different coordinate system, like cylindrical or spherical. Now we're going to look at more general versions of this. So maybe you come across a problem where cylindrical doesn't cut it and spherical doesn't cut it, and you need to just kind of make up your own. So that's what we're going to look at in this section. But first, I wanted to tie together the idea of the Jacobian with this surface area element that we saw back in section 15.5. So remember, if we're parametrizing a surface using some function r, so this has got like an x, y, and z coordinate, and it's over some parameter domain, then we have a picture that looks something like this, right? So here's our uv domain, our parameter domain, and then r is mapping it into R3. So R3 space here. So in this case, it's kind of bending the surface and wrapping it around, and this little patch here is supposed to get mapped to this little patch here, and so on and so forth. And I had an argument for why the area of this little patch right here, the distortion that it undergoes, should be the partial derivatives with respect to u cross the partial derivatives with respect to v, because that gives the area of that little infinitesimal parallelogram, right? So we compute that cross product using the usual formula, and then we have our area element, and dr is going to be the absolute value of that vector with respect to area, so du dv or something like that. Okay, so now let's look at how this relates to what we did when we set something up in polar coordinates. So let me bring in a picture. So here's how we set something up. Maybe I should label this. So to sort of set up an integral in polar coordinates, we have this kind of a picture. So here x is a function of r and theta. In fact, it's r cosine theta, and y is a function of r and theta. In fact, it's r sine theta. And we could imagine that some region that looks like this ends up looking like some sort of sectorial region looking like this. Yeah? And so in this situation, our transform r, and this is one of the reasons why I hate this notation. So bold r of regular r theta is going to be x of r theta, y of r theta, or more explicitly, it's going to be the mapping r cosine theta, r sine theta. Okay, so that's our transformation. I'll call this a transformation. Another word for this is you can think of it as a parametrization. The distance is mostly psychological. Okay, and then we can also say like, oh, well then how is it that this worked for cylindrical? Well, for cylindrical, we just have the same kind of idea, except that we're mapping now from a two-dimensional domain, parameter space, into a three-dimensional world over here. The only thing is, we're only mapping it onto the sort of ground floor, the xy plane in there. So if we look at the coordinates for this, our bold r of r theta looks like x of r theta, y of r theta, z of r theta, but actually this, oh, I forgot to close my parentheses. Actually, this part here is going to be 0 when we're doing setting up a plane region. So, in other words, when we're doing just changing the shape of the domain over which a function is integrated, right? So, what that means then is that if we look at bold r sub r cross bold r sub theta, then this guy's going to be I, J, K vectors, and then we've got xr, x theta, and then, oh, these don't depend on z, so there's going to be a 0 here, and then we're going to have yr y theta, and then we get a 0 also for that one. And so because they're just mapping into the coordinate plane z equals 0. Maybe I should have said that explicitly. Let me put that over here. So this is lives in z equals 0. And when I say lives in, I mean the range of our parameterization, the range of our transformation. So then let's see, so when we work this out, from the cross product formula, it ends out that we just end up extracting this subdeterminant right here. So this ends up xr x theta yr y theta times k hat. So in other words, it's the vector that looks like 0 in the first, 0 in the second, because there's no I component and there's no j component. Maybe I'll put that in here in silly blue, so you can just ignore it. And then we've got xr y theta minus x theta yr. And this is, when we go to take the size of this vector, this is exactly the part that we end up using. So this gives us our Jacobian and that's the one that we use for doing setting up integrals.